converter. So the buck converter is a DC-DC converter that uses a switch inductor and typically has a capacitor at the output. This is the basic topology for a buck converter. Here we're going to assume we have a constant input voltage and that our load is a resistor. And we have a capacitor at the output to help maintain that voltage. Notice we have two switches here. One is a MOSFET, and we call this the active switch. This is the one that we control. We can control the signal and turn it on or off. And then we have a passive switch, which is a diode. And of course we have an inductor here. So the buck converter takes a higher voltage and the output will be lower than that voltage. So we're bucking or stepping down the voltage. We just said it switches between two states. Let's look closer at how the circuit is represented during those two different states. So the first state is going to be when S is on. And here's a diagram of a switching signal. So when the switch is high, it switches on, this will be closed. So let's draw that diagram right here. So if S is on, then we know that this will be closed. So let's just draw that in here. So we have this switch, active switch, is on. So S is on, and we have our positive voltage here at our input, and that is Vin. And the other components are all the same. The resistor, capacitor, and inductor are all connected in the same way. It's just the switches that we have to figure out if they're on or off. So this area is where the diode is, and you have to say, is this diode going to be on or off? Well, if we look at the voltages here, we see because this is on, this voltage on this node will be the same as Vn, and this voltage here will be ground. Again, we'll just add a ground for consistency. And you see the voltage across here, this will be high voltage, and this will be ground. And that means that this diode is reverse biased, meaning that it will not be on, so it'll be open. When this switch is now off, which means it must be open, so here we have an open circuit, and the question is, this switch, which is the diode, how is that going to act? Is that going to be on or off? Well, it depends on the current through the diode. If current is flowing through this inductor, if it's in CCM, we can think of it as a constant current source, which means that if current is flowing through here, there must be a path for it to go through. Since we know this is open, current cannot flow through there. So the only other path to go through here is actually to go through this diode, and luckily the arrow is in the correct direction, so it will go through here and we'll turn on the switch if we are in CCM. If we happen to be in DCM and we're at the region where current stops going through the inductor, then the switch will turn off again and you'll just have a completely open circuit. But for now, let's stick in continuous conduction mode. So for that, we need to make that assumption. So Valerie is here keeping track of all our assumptions. So we are going to assume that we are in CCM, so continuous conduction mode, such that during S off, this will be closed. So this diode, which is also called a freewheeling diode, will also be on. So we mentioned before that the buck converter has a relationship between the input and output voltage. We know that the output voltage will be lower than the input voltage, but how do we know, and what determines this ratio? The answer is that we control the duty ratio, the time that we are in the on state for this switch relative to the total period. So our control variable is actually D here, and in our version, this version, our input is constant, but our output is not necessarily constant. We have a capacitor that will maintain the output voltage, but this voltage can vary. So to get the relationship between the input voltage and the output voltage, we need to derive some sort of equation. First, we need to make a few more assumptions. So we are going to say we are assuming we're in continuous conduction mode. We are also going to assume that we are in steady state operation in terms of the average value. So here we'll put SS, steady state, average. And this average means over this period, the average value will be constant. Within a period, the values will be changing, but the average value will be constant. This means that the average values of our dynamic components, which is the inductor and the capacitor, that dynamic component will be on average constant. So for the capacitor, this means that the voltage on average will be the same. So here we can assume the average voltage is constant, and we're going to assume that the capacitor is large enough such that it's not going to change the voltage significantly over one period. Okay, with that assumption then, we go back to our inductance and our inductor current, and we will draw an approximate waveform. And because during S on, we have the voltage over the inductor will be V in minus V out, the average value, then we know it's going to be going positive in this direction. And the angle here will be V in. We're just using I. VI minus the average value of V out over L. And then because we assume it's in steady state, the average value must be the same. So this, over one period, we have to return to the same exact point. So we're going to approximate this here. That means that this curve will go down like this, and this point and this point have to be the exact same point. Okay, let's look at the equation here again. The inductor voltage in this case is going to be negative V in. So we're going to go, negative V out over L. So if we look at this, we do see that the average value would be constant. So for this condition, this is approximately what our inductor current would look like. So we're going to write the volt-second balance equation over here. So during this period, if we want to calculate how much this inductor current has increased, we can look at this slope times this time period. So let's write that over here. VI minus the average V out over L, so that's this slope, times this time period, which is just D times T. And then we know that this rise has to be equivalent to the drop here. We are going to take a negative here and look at this decrease in the current over this second time period. So here's the equation. We have a negative of this times this time period. So negative of a negative is positive, and then the average of V out over L. Then we multiply by this time period. We want to put it all in terms of D for simplicity. So we can actually rewrite this period from here to here as 1 minus D times T. Alright, so this is our volt balance equation, and this must hold true for continuous conduction mode and average steady state. From here we just simplify. We can cross out some similar values on both sides. We see L is on both sides. We see T is on both sides. And now let's expand these equations. So multiply D out. So we have D, VI, minus D times the average value of V out. This is equal to, multiply these out, average V out minus D times the average V out value. Okay? Here again, we can simplify. We see that this is the same on both sides. Simply get rid of that. And we are left with a very simple equation. D, the duty ratio, times the input voltage is equivalent to the average output voltage. We can also rewrite this as D equals the average Vout over the input voltage. So we've taken this kind of complicated switching circuit and we've boiled it down to a very simple relationship between the input voltage and the output voltage and this duty ratio, which is the control of this switch. Remember, it's the on time of the switch relative to the total period. So if, for example, we have a 10-volt input and we want to bring the output voltage to 5 volts, take our values, plug them into this equation, 5 output voltage over 10 input voltage equals 50% duty ratio, or 0.25, which is really quite amazing. We can just put a duty ratio here on this switch and we can control the relationship between the input and the output voltage. Valerie will remind us that this equation is only true when we are in continuous conduction mode, CCM, and we're in steady state in terms of the average values. All right, that's the basics for a buck converter.